Advanced Statistical Process Control deals with situations where traditional control charts can be misleading. Most SPC examples assume that measurements are independent and that you're monitoring one thing at a time. But in the real world, processes are often more complicated. Sometimes, several variables influence each other. Other times, today's result is heavily influenced by yesterday's result. These situations are known as multivariate data and autocorrelated data. Let's start with autocorrelation. Imagine you're monitoring A and E waiting times in a hospital. If today's waiting time is high, tomorrow's waiting time is likely to be high too, because the backlog carries over. The data points are connected. This creates a problem. Standard control charts assume each point is independent. When that assumption is broken, the chart can generate false alarms or hide genuine process changes. A useful way to think about it is like ocean waves. If one wave is high, the next wave is likely to be high too. You wouldn't treat every wave as a separate event. The same principle applies to autocorrelated process data. Now let's look at seasonality. Suppose an NHS trust tracks waiting times throughout the year. Every winter, respiratory illnesses increase demand. Every summer, staffing levels may drop because of annual leave. A traditional control chart might show repeated special cause signals every December and January. But those signals are not necessarily process problems. They're predictable seasonal patterns. To understand what's really happening, we need to break the data into components. Every time series can be thought of as 4 parts. The first is the trend. This is the long-term direction of the process, whether performance is improving, worsening, or staying flat. The second is seasonality. These are regular repeating patterns such as daily, weekly, monthly, or yearly cycles. The third is cyclical variation. These are longer-term waves caused by factors such as economic conditions, business cycles, or equipment life cycles. The fourth is residual variation. This is the random noise left over after everything else has been removed. This is the part SPC is most interested in monitoring. Think of it like listening to music. The trend is the melody. Seasonality is the repeating rhythm. Cyclical variation is the rise and fall of the whole song. Residual variation is the background noise. To find genuine process changes, we need to remove the predictable patterns first. A simple 4-step approach works well. Step 1. Plot the data. Look for obvious calendar patterns, repeating peaks, trends, or cycles. Step 2. Strip out the seasonal effects. For example, compare each January against previous Januaries rather than against the annual average. Step 3. Smooth the trend. Moving averages can help reveal the underlying direction of the process. Step 4. Chart what remains. Apply your control chart to the cleaned-up residual data. Any signals that appear now are far more likely to represent genuine process changes. Let's return to the NHS example. The original control chart appeared to show frequent special cause signals every winter and summer. After removing the seasonal pattern, the team discovered 2 genuine process changes. The first was a deterioration following a computer system change in March. The second was a significant improvement after a new streaming protocol was introduced in October. Those important signals had been hidden by seasonal noise. This is the key lesson of advanced SPC. Before reacting to control chart signals, ask whether the data contains trends, seasonality, cycles, or relationships between variables. If you remove the predictable patterns first, your control charts become much more powerful and much more trustworthy. The goal is simple. Stop reacting to noise and focus on real process changes that matter. This topic is covered in our Lean Six Sigma Black Belt course. Enroll today and add a word-recognized accreditation to your CV.